and welcome to our 12th annual Sailfish Point fundraiser. I'm Dick Landesman, Jane's husband for 57 years. Jane and I began to raise funds for cancer research shortly after our son Keith passed away from cancer 17 years ago. Initially, we ran a golf tournament and silent auction in Westport, Connecticut. And then Jane started a small ladies' night out for cancers. Some women here were involved in that original discussion meeting. We started an awareness at Sailfish Point, which expanded to this community-wide day and evening. We thank you with your generosity and support. We have raised now nearly $3 million. And you do deserve some support. When we started, we were looking for an organization to support, and when I mentioned immunotherapy and Cancer Research Institute to my oncology colleagues in Connecticut, they were very skeptical. How glad we are now to see that they were very wrong about the value of immunotherapy in cancer treatment. Cancer Research Institute was founded in 1953 and is now the global leader in supporting and coordinating research aimed at harvesting the immune system's power to conquer all cancers. Currently, 30 or more cancers are treatable with immunotherapy. And I know several people here have had immunotherapy treatment for their cancers and have done well. Several years ago, CRI's Scientific Council Director, Dr. James Allison, won the Nobel Prize in medicine. All cancer treatments start with basic bench research. At your table is listed all the researchers we have all funded over the years. I think one thing that you should be well aware of, you know where your money has gone when you have donated to Cancer Research Institute. It's to support the research fellows that are listed on the sheet in front of you. But you did not come here tonight to hear me speak. Let me introduce and welcome back to Sailfish the CEO of Cancer Research Institute, Dr. Alicia Zhou. Alicia has a BS in biology from MIT, a PhD in biologic and biomedical science from Harvard, and she completed her postdoctoral research in cancer biology at the University of California in San Diego. Very impressive credentials, I must say. Please welcome Alicia to Sailfish Point.
I think I'm good. Can everyone hear me? Yes. Great. I'm going to try to walk around a little bit because I know we have two crowds here and I want to make sure folks have the opportunity to hear me and see me. Please feel free to interrupt me if you have any questions as we go. Thank you so much to Jane and Dick for hosting this amazing gathering here at Sailfish Point. It's great to be back here with you all. It's amazing the impact that you all have been able to have for us at CRI, but for the field of cancer immunotherapy at large. I really appreciate all of the investment in our early trainees. You can see the names of the trainees that you've supported and on the table in front of you. These are young researchers who really came into this field with a dream of doing something important with their hands and their brain to make sure that they could be working on the problems that would help bring cancer immunotherapy and cancer treatments to all patients, and your investment in them is what's propelling them and keeping them able to continue to do this kind of work, especially right now when federal funding is very difficult to come by, and we've seen actually more than twice the number of applications this year for our CRI postdoctoral fellowships, as well as for many of our other grant mechanisms. It tells us that there is a need. There are all these trainees out there who want to be able to follow their dreams to become cancer investigators, and I really appreciate and have so much gratitude to the folks in this room who have continued to support that dream, so thank you. I do want to spend a little time talking a little bit about sort of the state of where we are today when it comes to cancer immunotherapy, cancer diagnosis. It's a little bit of good news, bad news kind of headline. So one of the good news pieces of this is that we are actually seeing a decrease in cancer mortality, and have seen a decrease in cancer mortality for many, many decades now. So actually, since 1991, we know that there's been a 34% decrease in cancer mortality across all cancers here in the United States. That's resulted and translated into about 5 million lives that have been saved because they have avoided or would decrease that cancer mortality rate. Now, what we know about that is a lot of that has to do with smoking cessation. That's actually been one of the big places where we've seen a lot of impact in terms of being able to bring down cancer mortality. We also are seeing incredible survival rates for now 4 of the most common cancers, including breast cancer, prostate cancer, melanoma, where we're seeing that the earlier stage you are diagnosed, the much higher your survival rate. And in fact, for breast cancer, a diagnosis of stage 1 breast cancer now is a 99% survival rate. At the same time, there are some troubling trends that are happening, and folks probably have seen some of this in the news as well. Just in the last 2 or 3 years, we are now seeing that colorectal cancer has become the leading cause of cancer death in patients diagnosed under the age of 50. So this is pretty surprising and something that folks are tracking, and really we're not really quite sure yet about the epidemiology of that. Why is that happening? But what we do know is that screening does work for colorectal cancer. What folks might not realize is that as a result of the increase in incidence in patients under the age of 50, the screening recommendation for colorectal cancer has changed. It used to be that you start your colorectal cancer screening at the age of 50. That age has now been decreased to 45. And if you have a strong family history of colorectal cancer or other cancers, you might even start at an earlier age. And that means then that we really have to think about prevention here and early diagnosis. What we know is that the earlier that we can catch a cancer, the more likely we're going to have good outcomes for that patient. And so one of the things that's important to recognize here is a lot of folks I know don't want to go to their first colonoscopy. It's not exactly one of the things that we look forward to. And so what happens is folks turn 45 and they say, oh, well, the age used to be 50, so I probably still have a couple of years before I need to go in. And what we know is that these patients that are diagnosed under the age of 50, they often are diagnosed with more aggressive disease than folks who are diagnosed at a later stage. And it has a lot to do with uptake of screening. So what that means is folks should definitely spread the word. It is important to get colorectal cancer screening done, and the age for average risk patients is to start at the age of 45. There are multiple ways you can do that. A colonoscopy is one of those ways, but there's actually now several non-invasive ways to screen for colorectal cancer, including the Cologuard test, as well as a FIT test, which you can get from your doctor's office. So there are all sorts of things that we can do to be more proactive about our cancer risks to ensure that we're able to help prevent late-stage disease and get treatment as quickly as possible. Colorectal cancer is a really interesting one as well for immunotherapy. It's actually one of my favorite immunotherapy stories that's come out in the last year. There was an amazing study that was done at Memorial Sloan Kettering, led by an investigator named Luis Diaz, who actually looked specifically at colorectal cancer and found that there are certain patients who have a biomarker that makes them a very good candidate for immunotherapy. And what they found is that they recruited about 100 patients into this trial, and they actually gave these patients immunotherapy before surgery. So typically immunotherapy happens after surgery. In this case, they actually administered the immunotherapy before surgery, and they found that in these patients, about 100 patients who had this biomarker, 80% of them did not have to have surgery afterwards. What we know is that when we find the right targets for immunotherapy, when we are able to activate the immune system to go and target these cancers and be able to treat these cancers, it is very possible to change the paradigm of how we think about treatment. And this is an excellent example of this. At the same time, I think colorectal cancer is one of the most difficult cancers to treat because there are some tumors that respond really, really well and others that don't. And we still have a lot of unanswered questions about how can we identify which tumors should have which combinations of therapies in which order in order to have the most efficacious outcome. So this is one of the areas that we're investing in at CRI. We just launched in January our CRI Discovery Engine, which is going to be our large data initiative where we are going to be generating a massive data set looking specifically at all the most commonly occurring cancers treated by all the most commonly used immunotherapies. And then we're going to generate single cell data across all of these combinations to be able to understand what is the right combination of treatments for certain cancers, what's the right timing of those combinations, and why do some combinations work and others don't. The goal here is that we know that the next generation of discovery is going to be AI enabled, and in order to be able to fuel that AI enabled future, we need to make sure that the foundation of data that's being used to train those AI agents is correct. And so for us at CRI, our goal here is to invest in these data foundations. And so very excited to have launched that in January, and we're going to be starting to generate data in the next several months. But I'm very excited here at CRI. One of my favorite things that we do is that we invest in scientists and researchers who I think really are on the cutting edge of what's happening in the field. And so I'm very excited to be able to introduce one of our CRI stars. The CRI Star Award stands for Scientists Taking Risks. These are scientists who are really asking the hard mechanistic questions in immunotherapy. And we want to ensure that they have the support they need to be able to flourish in their careers. We do 5 stars a year. These are truly some of the most exceptional scientists that we see every year. And tonight we're joined by one of our CRI stars, Dr. Haydn Kissick. He's going to share a little bit about the work that he's doing at Emory.
Thanks, Alicia. All right, we got this? Wonderful. I thought I'd tell you a little bit more about myself before I started giving an immunology lecture. I often wonder when I'm driving to places like this, how did I get here? You'll notice the accent. I'm from a city in Australia called Perth. When I looked it up, it is the furthest city in the world from here. You can go east or west, it doesn't matter. It is the furthest city you can go to. So I came to America about 14 years ago. And the reason I came here is probably the same reason a lot of you are here today. And so I want to tell you my story of how I became a cancer researcher and what we've done. When I was 10 years old, my mum was diagnosed with cancer. It was ovarian cancer. It was very bad. She had to have surgery immediately. It affected her life a lot. She wasn't cured. She had chemotherapy for the next 10 or so years. And so I know cancer from that perspective. That's what I grew up with. I know what infusion friends are. I know what happens when you get chemotherapy. I know how you lose your hair and fingernails. I know when friends stop coming around because of they didn't make it. And unfortunately, I also know what it's like to lose a parent to cancer. So in 2006, after 13 years, I lost my mum to cancer. They didn't know what it was. It was similar to what Dick's story is. At that point, it was an undescribed cancer. They'd lost track of, she had metastases to different tissues and all sorts of things. We didn't know anything. We didn't know about the genetics of it. There was no immunotherapy. There were no options. And very honestly, I remember the last conversation with the doctors, which was, we've got nothing left we can do. And so that's why I'm here, because I think like all of you, you think, what can I do? You've all had this situation, I'm sure, a family member, a friend, yourself, a a partner, a parent who has had this, and you've asked yourself what you can do. And what I'm going to tell you is what you have done and what you can keep doing and what we're doing together. We're going to fight this together. So at that time, I was about 22 or 3, and it was time to choose what I was going to finish my undergraduate. What was I going to do? There was only one choice. I was going to do cancer research. And so I took that chance, and it happened to be that it was immunology. I didn't know that was a good idea at the time. When I gave my proposal, I said, hey, this seems like a good idea. This is what I believe I can do. I believe I can fight cancer like this. I was told that this is the worst idea. You should give up on this. Cancer immunotherapy is never going to be a thing. We've tried this for 100 years. And like it sounds like Dick wanted to give money to CRI, people were very, very skeptical. And Jim Allison, who did win the Nobel Prize a few years ago, was basically treated as if he was an outsider. He had trouble getting research money. I don't know if CRI funded him, probably, but many foundations funded him because they believed in it. And that was what got me started. So in 2006, I gave my proposal. No one liked it. I worked on it. I made my way through the PhD over 3 or 4 years. And the year, within a few months of me graduating, was when the first immunotherapy drugs were approved. It has been this was 2010 or 11. At that time, I realized that Perth probably wasn't going to be a place where we cured cancer, and I had to move to the US. I did email Jim Allison, and he did not respond to me. Since then we've met. He's actually extremely nice, and I think if I'd tested him more, he would have. But I made my way to the US. I believed I had to be here where all the research was happening, where the best things were happening, where I could really contribute and do something. So I applied for maybe 100 jobs. I moved to Harvard in 2011, where I started working on cancer vaccines, which I still have huge hope for. And then in 2014, I moved to Emory, where I started my lab to understand cancer biology and the immune response to cancer. I will tell you a little bit about it. I will not give you a full lecture. We study a type of cell called a T cell. This is, I think, one of the most incredible cells of your body. So when you get sick with an infection or really anything, the T cell is the cell that kills the thing that has taken over your body. So when you get COVID or influenza or something, you've got a few hundred of these cells that will notice that and say, hey, that's not meant to be here, we're going to kill it. And what they do, from a few hundred, you have trillions and trillions of cells in your body. These cells expand to billions of cells. They go from this small little number, they divide every 4 hours, almost like bacteria. They're taking over. If you look in your blood, they're everywhere. And they go into every single tissue of your body, and they find where the virus is, and they kill the cell. If it's in your lung, they kill it. If it's in your liver, they kill it. Brain, kill it. They do not care. And then a week or 2 later, you feel a bit lousy because they've killed a lot of your cells. But they've found every single place in your body where that virus has gone and managed to kill it. The same rules that govern that cell to kill a virus are how that cell also kills your cancer. So the drugs you've heard about, PD-1 and checkpoints, they work on this cell called a T cell, and they help it do the same thing it does against a virus to the cancer. What we've been studying is something called a stem T cell. And so what is so exciting about this, you guys have heard about stem cells. They can regenerate an organ or regenerate damaged tissue, nerves and all sorts of things. The cell that we've found is called a stem T cell. And what's exciting about it is just a few of these cells, maybe a couple of hundred, can regenerate those billions and billions of cells that are the cells that can kill your cancer. And so what we find, though, is that in cancer, they're present. They're in every patient who has it, in their tumors, in the lymph nodes around their tumors. You guys have all heard about lymph nodes. That's a very important part of your immune system that is, helping the immune system notice the cancer. So every patient has this cell, and it's capable of tens of thousands, millions and millions of fold expansion, but it's being held back. And it's a mechanism we don't know yet. We know the cell can do it. It can make all the cells to kill your cancer, but it's just not doing it right now. Our current therapies, PD-1, CTLA4, all these things you've heard about, don't quite work on it yet. We're starting to find little things. This was last year. This is new stuff. We've just worked it out. So we're trying to find new ways to tell that cell, hey, you can do so much. You're a stem cell. You can make the whole immune response against cancer, but you're not doing it. Let's find how you can and tell you how to do that. And that's what CRI funded me for. We're really excited about it. We're trying to, make this happen. I'm going to tell you a little bit about that in a second. Because what we're living through is something that doesn't happen very often. It is a true revolution in medicine. So when my mum died in 2006, no genetics, no immunotherapy, didn't really know how to diagnose these things, and now it's 20 years later. 5 years ago, one of my closest friends at Emory was diagnosed with a cancer, uveal melanoma. So it's a very bad cancer. It's a melanoma that's in your eye. And so he's a surgeon. He noticed, he's like, hey, I can't see properly. I'm having trouble cutting. They cut it out. They did the genetics on it immediately. They're like, we know exactly what the genetics of your cancer is. You have a very high risk in the next few years of getting metastatic cancer to your liver. So because of that, every 6 months he went and got a scan, he checked, and then unfortunately one day they noticed, hey, you've got metastatic uveal melanoma. This is a terrible diagnosis. It's very bad. In the year, or the 2 years between the first diagnosis, the first cancer and the metastases, a new immunotherapy was approved for this cancer. It's totally different from a checkpoint therapy. It's a brand new type of way to kill cancer. We call them T-cell engagers. So that cell I was telling you about, the T-cell that kills everything. What it does is it sticks to the cancer and then lights it up like a beacon and says, hey, T-cells, kill this. And it's been 2 years now and he's disease-free. So this is the revolution that you have funded, from people not believing me, that telling a student that their project was stupid, to now all our newest drugs, every year there's something new that's coming out. This was uveal melanoma was the first one. Every cancer they're testing these T-cell engagers now. New ones will pop out every year. So we're living through a time when cancer is getting cured, and it's a very, very exciting time to be part of that. What I want to tell you is what I think is the next step of the revolution of cancer. You guys all know about RNA vaccines and the therapies that we had with this. This was an incredible thing. It was great for vaccines. We realized we could make a vaccine really quickly. We could treat a lot of people, and we did it very, very cheaply, which changes the way we think about medicine and clinical trials of new drugs. So not just vaccines, we can do lots of things. We can make new drugs like PD-1 you can make with an RNA. All the new targets that we think are maybe good ideas, but would usually take 10 years to test. We can make them now, we can test them in 1 or 2 years. Alicia was just telling me about talking to the FDA about changing how we regulate these things so we can do this quicker and do it faster. So my friend who had uveal melanoma, he used to be the dean of our medical school, he decided, hey, Emory should do something. We should try and do this. So we're going to build a facility in the next few years so we can test these ideas of treating patients immediately with drugs that we come up with from these ideas, about these stem T cells. How do we make them do things? We're going to make drugs at Emory, test our patients with things that we can do right there on the day. To be a new way to do it, because I think that's what we all want. We're all here to do something about cancer, and that's what we're doing now. He was affected by cancer, he wants to do something. I want to do something. You're all the same, you want to do something about this. So I think it's an exciting new time for that. The last thing I want to say is really how I got here. So you heard about that path. And what I want you to know is really, that doesn't happen. I don't just turn up and move across the world. When I came to America, the lab I moved to was funded by a foundation to do a cancer vaccine project. It wasn't the NIH, they got money from a foundation. So I was brought over here and given the opportunity to do this because a foundation has supported them. When I moved to Emory, I was given money by the Prostate Cancer Foundation to continue the vaccine work that I was doing in prostate cancer. I could never have done that if a foundation hadn't supported it. When I got to Emory, Swim Across America funded our lab to get started. The first student who worked on this and found this was funded by Swim Across America. They did make me swim for the money. I had to swim a mile in the water. Well, CRI doesn't do that. And then most recently, this new work I'm telling you about is what CRI funded us to do. And it funded new students like you've all heard. So my dream was, maybe I'll be the one who cures cancer. And it's been people like you guys who believe that this can happen. You've funded these people. Alicia's got 7 or 8 names on the back of that. They're me 10 years ago. All of them will grow up to do incredible and amazing things, make new facilities that treat patients in new ways. We don't know. And so really, I just want to thank you. You've all given me the opportunity to be here, to do new things, to fight cancer in new ways, because I wanted to do something just like you. And I think it's one of the best things we do as people. We're not asking for anything back. We're just trying to do our best to help the people around us. And thank you very much for that opportunity. You've really helped me a lot.
Not be so close.
You're good.
Hello? Oh, great. Okay, so the goal here is to be able to actually help answer your guys' questions about anything that we've covered today, or any curiosity that you have about things related to cancer prevention, diagnosis, treatment, immunotherapy, the work that Haydn does. So I'd love to open it up for any questions from the audience that folks have for Haydn.
So, immunotherapy immunotherapy, is the CRISPR technology of using proteins considered part of immunotherapy?
We use it in immunotherapy. So that belongs to a field we call molecular biology. So it's a tool that lets us, change how the molecules of the body work. And we apply that to the immune system to trick it into ways to do the things we want it to do.
So that therapy doesn't go after the cancer itself, it does it the other way you described it with the T cells?
So CRISPR therapy can be used for many, think of it like a hammer. Yeah, you can build a house or you can build a boat. And and we're the boat builders. We're boat builders. We use it. So we use it to modify the T cell to do what we want it to do. We can edit its genes and say, hey, kill cancer, do these things. And so that's an incredible technology that is just letting us, the therapy we're trying to do with this RNA, we're trying to basically reach into a single cell and touch a little specific part of it and say, do this. And it's, it's a single molecule. And the CRISPR technology is absolutely related to that, and we sort of use that to do that.
Wonderful presentation. I much appreciate it. Thank you.
I'll just add on top of that, I think CRISPR is one of the most interesting types of tools that we have today for modern medicine. The way that it works is it lets us cut up DNA and insert our own version of DNA, replace it. And so this type of technology is called gene editing, and we can use it for all sorts of different disease types. But actually, in immunotherapy, one of our other stars, his name is Alex Marson. He's at the Gladstone Institutes at UCSF. He actually just recently did some really cool work where he showed that you can actually use CRISPR to turn things on and off in T cells. So now you're thinking about not just being able to change the genes in the T cell, you can actually think about how you're changing them over time and modulating how that T cell is being activated or silenced over time. So CRISPR technology, I think, is one of the coolest things that has been discovered in the last several decades. I think one of the best things. I mean, it won a Nobel Prize, and we're really happy to see it being applied towards immunotherapy. Other questions?
Thank you for your presentation, and thank you for the work that you do. Is your work that you're doing now equally as applicable to pediatric cancer as it is to adult cancer?
Yeah, absolutely, and we absolutely look at that. So we've looked at some pediatric kidney cancers where everything seems the same. Kind of the nice thing, as Alicia or Dick said, 30 cancers are now cured with immunotherapy. The thing that's about your immune system is it doesn't know if it's a different type of cancer, it just knows something's wrong. And so when we get something right for one cancer, it has often been the case that it's exactly the same or very, very close for the other cancers. And so most of the pediatric tumors we're looking at seem to follow the same rules as the adult cancer equivalent. So yes.
One of the other really cool stories in IO in the last year is actually about pediatric cancer. It's diffuse midline glioma, which is a very aggressive brain tumor that occurs in pediatric patients. Unfortunately, the survival rate is very, very low in the single digits. But there's been some really interesting work coming out of Stanford, and there's an investigator named Crystal Makel, and she and her collaborators there have demonstrated that they can use CAR T therapy, which are these engineered T cells, to be able to treat these pediatric patients. They've done a phase 1 trial. There were 11 patients that were in that trial, and they found there was actually a positive response in 9 of those patients. 7 of them had their tumors shrink. One of those patients was diagnosed when he was 16 years old with a survival likelihood of less than 10%. That boy today is still alive and a sophomore in college. And this is the type of outcome that you can see when you see some of these really promising immunotherapies coming to market.
Oh, okay. Do you feel like there is kind of a mutation that keeps on going on with cancer, and how it's related to maybe our environment? Is there anything about that? So you're always kind of racing to try to, cure the cancer, but then the cell mutates or the virus mutates, and then so you have this kind of race that's going on all the time.
Yeah, so it's basically like evolution, right? There's a selective pressure, and the cancer tries to get away. This absolutely happens. So we can track one of these things, this sequencing the genomes of patients for basically, a couple $100 now. We can track that over time and see how that happens. So some of the vaccine trials where now we're able to make a vaccine for a patient, and we make a vaccine against their mutations. We say, hey, these are the mutations in your cancer. We're going to make your immune system kill those. What we notice is if it works for a long time, new mutations start to pop up. But we are fast now. So one of our projects at Emory is so as a patient has a tumor, a biopsy comes out, and by the time they come to the clinic the next day, we have the genetic information of that patient. So the new mutations, we just know them. And the ability for us to make these vaccines and therapies within a couple of weeks now means we are faster than the cancer. So the technology has allowed us we were losing that for a long time, and I think now we're ahead of it, and we're able to beat it.
I want to thank you for your presentation. It was awesome. Maybe you could share with us how AI is either increasing the speed of cycles or reducing the number of cycles required to get to efficacy for various solutions.
Yeah, this is a really good question. So I think we all know that AI has changed the way we think about how we interact with the world. I think the places where we've seen that the most has been in the way that we communicate, in the way that we acquire knowledge. And folks have been now using these large language models to be able to sort of accelerate their cycles. We know that this technology is going to be coming for every single sector, and I think one of the questions I get asked all the time is how is AI going to change biomedical discovery? I think it will fundamentally do that. In fact, we've already seen the effect of AI in biomedicine. Last year, the Nobel Prize was given to AlphaFold, which is this protein folding algorithm that has changed our ability to very quickly understand what is the protein structure of proteins that we otherwise wouldn't know. We know what their sequence is, but we don't know what they look like in 3 dimensions. And AlphaFold has changed the game, which means it's changed the way we can think about doing drug discovery at the protein level. I do think that this is going to revolutionize the way we think about discovery, but what we also know about every single AI model is that it's garbage in and garbage out. And that means that you have to train it with the right data going in. Biology is incredibly complex, and unfortunately, even as human researchers, we have a very, very low understanding of all the pieces. We're still discovering. I actually think what's most exciting about large language models is their ability to do multiple massive processing in parallel. And I think that the massive amount of data in biology is the right problem to be attacking. And so that's where I do think it's important for us to be investing in the right data sets, truth sets, foundation sets. They're going to train these foundational models so that they know what is truth and what is not truth. What we know about AI is that as powerful as it is, it can also hallucinate, it can make things up, and then you have to be able to correct. You have to be able to say, no, not there, it's here. So the way I think about it is the way that ChatGPT and Gemini have been trained up on Wikipedia, the internet, Reddit, Shakespeare, the New York Times. I want the CRI Discovery Engine dataset to be the Shakespeare of immunology. Let this be the truth set that helps to train up these large language models for immunology.
My question would be, we've gone over we haven't gone over anything here actually. We talk about your successes and things. My question is, there might be people, when you talk to cancer doctors throughout the world, how many of them are really into immunotherapy that you're talking about? And if a cancer patient is interested going to your side, how do they become patient or whatever? We're talking, you talk theory, I'm talking about the poor guy out here that's got colon cancer and would like to talk to you, for Christ's sake.
So in the US, most patients are getting our best immunotherapy right up front. So our colon cancer patients, they all get immunotherapy. It's become the absolute mainstream of therapy for patients now. But that hasn't happened across the whole world. So I was in India last year. They can't afford to give these drugs. It's too expensive. So they're testing half the dose, given half as often, and it works just as well. And so, we're maybe paying 4 times more than we need to for these things. And so there is a big need to get this out. I'd say in America, it's pretty established. The doctors are giving it. There are guidelines for doctors to follow, and this is right at the front of most of their guidelines. And some of the places, it needs to get out to the rest of the world to help, potentially millions of more people.
Are those some kind of drugs that they feed you in the beginning, or?
Was that say again?
Some kind of drug that they give them to slow the cancer down, or?
Yes.
So this is immunotherapy?
Yep.
And if that doesn't work, do they go on, or do they?
So there's
is
a lot.
there some continuum that they can contact you that they don't know about, for example?
So there's a good continuum. So, we try one drug first, then we usually put a couple together to try to be more intense. If that doesn't work, then sometimes chemotherapy and immunotherapy together will be, really good and work. So, doctors will intensify the treatment as they go. If it doesn't work, then depending where you're at, you can ask the doctors about clinical trials. So every institute's trying new things. Everyone's trying new things. And if you want to look wider, then there's a website, clinicaltrials.gov, which will tell you every single clinical trial happening in America. And you can contact the doctors, you can contact people at CRI to find out about these things. Because it's happening everywhere. It's not theoretical at all. It's happening everywhere. And there's new things being tried all the time. But lots of good options first. You don't need to immediately go to a clinical trial. There are a lot of good things to try first.
And if someone is interested in a clinical trial, we do have the CRI Clinical Trial Finder that actually goes to clinicaltrial.gov, which is this massive database, and helps you navigate that and find you the trials that match to your specific cancer type. So instead of you having to go through that, we do that for you. So if folks are interested afterwards, please come and find me. I'm happy to give you more information about that.
You mentioned the data sets, and working with AI. And you mentioned already what I was thinking, the garbage in equals garbage out. Is there a mechanism or is there a process where you're vetting that data and what data is used and what isn't? I'm sure there is, but is there an authority, a traffic cop, if you will, to look at this data? Because if it's not managed, you're going to get garbage in, garbage out.
Yeah, this is a good question. And so one of the things that I always think about, you'll always hear this adage that all models are wrong, but some are useful. And so the thing that we think about when we think about generating data is, what is the model that you're using? And then what do you know are the limitations of that model? So actually, for the CRI Discovery Engine, for example, the way that we're actually approaching that data set is we are prospectively generating that data. It's not actually looking at retrospective data. We're not going back to published research. We're actually going to generate brand new data. The data are going to be generated from some of the most commonly studied animal models of cancer. So these are the ones that pretty much every investigator across the world uses. And we're going to be looking at the most commonly perturbed immunotherapy pathways. So these are the genetic or molecular pathways that are being perturbed most frequently. And what that means then is, as we generate this data set, and then if a model is also being trained, if a large language model is also being trained in parallel, the idea here is that the output of the model can then be fed back into the bench science to validate. So if the model predicts something, instead of just taking that prediction as truth, you can go back to the bench and ask, is it true? And so it becomes really important. I do want to also say human data is incredibly important, but also I think sometimes folks think of humans as somehow the best model, and humans also suck as a model system in many ways. And so, again, all models are wrong and some are useful. You have to recognize when human data can be really useful, when animal model data can be really useful. I think in 10 years' time, certainly, hopefully 5 years' time, every bench scientist will actually be looking at multiple model systems, including an in silico model. They're going to be looking at an AI prediction model in addition to their animal models and human data to actually think about how they solve their problems. I don't think it's a one model to rule them all. I actually think it's going to be, our scientists are going to recognize how to use all of these tools together to be able to get to an answer faster.
I just want to thank you and your colleagues for the great work that you do. It's fantastic, and obviously a heartfelt thank to Dick and Jane for making a difference. You've spoken very eloquently about the road ahead and how AI and big data agents are going to help us, which is terrific. I was just wondering if you could just spend a minute to imagine what you might see on the horizon coming from quant.
Oh, interesting. Do you have something off the top of your head here?
Quantum computing,
Yeah.
for those who were trying to figure that out.
Yeah. I think my feeling is that I think that what quant can do for us is to massively accelerate the ability to do large compute. And I think that a lot of what we've been limited by today has been the compute. So I think it actually did take us being able to have these types of transformer-based large language models to be able to actually ingest the scale of data that biology requires. If you think about sort of the trillions of cells in your body and the trillions of DNA molecules that are in them, and that's just DNA. There's proteins that come from that DNA, there's RNA that comes from that DNA that makes proteins. They all talk to each other, and the cells all talk to each other. It becomes a massively multidimensional problem very, very quickly. I do think that as a result, we're going to have to solve the compute side of the problem, and I do think that quant might have something to do with that.
Hi. Does immunology actually cure cancer, cancer, or does it just extend your lifespan? Because I've had a cousin who was involved, he lasted another 6 or 7 years, and I know another person who had a son with pediatric cancer. His son lasted another 20 years, but the cancer came back. So is it curing cancer, or is it just prolonging people's lives?
I think we'll both have the same answer. Yes. So depending on the cancer, depends how many people are cured. And cured can mean so many things, right? So I think a 5-year disease-free, is that what? Yeah. 5 years disease-free is what the technical term of cure means. But I think we all want way longer than that. Most patients who make it to 5+ years have a very good chance of never seeing the cancer again. So I think for lung cancer, it's around 20% of patients don't see the cancer again. Kidney cancer, it's about 15. Melanoma, it's higher. I think, yeah, like 50% of melanoma patients don't see the cancer again. But, if you're a 40-year-old and you have cancer, you've got a long time to wait and see what happens up. And like the question over here, the cancer adapts, right? Like if the immune system's killing it, then it learns new tricks and it can pop back up. So sometimes it will come back up, and it's up to us to learn what the new trick was and have the new tools in place to do something. And so, let's say 20 to 50%, depending on cancer, we still have a lot to do. Like there's a huge number of patients who have no benefit, comes back in 2 years or whatever. It's not done at all. But in the past, I don't think we had many patients cured at all there were some, absolutely, from some cancers. And then, in the late 90s and early 2000s, we started to get some really good drugs that were doing really well. But this is across the board, many patients are being cured.
I think the other important thing to think about here is that ultimately it's some combination of technologies that are going to help us get to earlier diagnosis, which will also get us to more cures. The reality is that the longer that a cancer has to be able to proliferate and potentially metastasize, much more difficult it is for us to develop drugs to go after them. So as much as we're working on the therapy side of things, I think there's a lot of interesting things that are happening on the early detection side of things that I think it's some combination of those together that will bring us to more cures for more patients. This is actually the area where I think cancer vaccines is the most interesting. You've heard Haydn talk a little bit about this. The way we think about cancer vaccines, you all get, hopefully, your flu vaccine every year, your COVID vaccines, you got your vaccines when you were a kid that makes it so that you don't get measles. These are all really important things that have trained your immune system to be able to recognize if you ever do get challenged with one of those viruses. We want to be able to do the same thing for cancer, meaning that we want to be able to predict what the cancer is going to look like. We're going to train your immune system ahead of time to be able to be ready for when that happens. Right now, in the space of cancer vaccines, the way that's happening is what Haydn has talked about, which is we try to understand the characteristics of your tumor. We sequence it, and we understand what are the genetic mutations that happen, and very quickly turn around and try to make a vaccine that's going to target those genetic mutations. I think there's also an interesting group of work that's happening, trying truly to look for prevention for cancer vaccines. Starting in pancreatic cancer is one of the places where that's been happening because there's a commonly mutated gene in pancreatic cancer called KRAS. And then there are certain folks who are born with a genetic predisposition for cancer, and there's interesting studies happening to see, knowing that these are patients that are likely to develop cancers, can we actually develop cancer vaccines for those patients where we know their lifetime risk of cancer is 50% or 80%? Can we develop a cancer vaccine for those patients that would be able to prevent those cancers? So there's a lot of really interesting work that's happening, but I do think it has to combine together with the early detection side of the work in order for us to really get more cures. Yeah.
I had a daughter that died at age 53, and she went to Mass General, and they gave her a magic pill, and she died. And she couldn't take the medication, and I think that was a big problem. She was this big, what are we doing to have medication that I think we take without the feeling that they're dying and the medication is doing them in worse than the cancer?
Yeah, I mean, that was like my mum, right? Like, chemotherapy, we basically poison the human to the point the cancer dies just before the person does. That's the dose tolerance. So up until about 2010, that was how we treated cancer. And it's truly terrible. We still have to do it sometimes, you know, because sometimes it works, like sometimes it does work, but in many cases it's not worth it. You know, would you take an extra year if you were in bed, couldn't do anything? Like, you know, my mum chose not to at one point because it was just too bad. Immunotherapy is not without side effects. It can absolutely have very, you know, they can be truly toxic, but most of the time it's not like that. You can live, I forget the exact stats, I'm going to mess this up. It's about 20% of patients have what we call grade 3 side effects. So this is things like rashes where you're a bit itchy, you know, like you might have upset gut, things like that, which is very uncomfortable. I don't want to make out like this is like totally fine, but it's not poisoning the patient to the point where they're about to die. So one of the best things about immunotherapy is the side effects are much, much better. It's more like having a, you know, like a sickness, because your immune system's active. You get a fever, you get sick and things like that. And that's one of the huge benefits. So that's why doctors often start with this, because the side effects just aren't as bad as your own immune system as trying to poison someone. So we all hear what you say. That's what we're hoping to do with immunotherapy.
Thank you.
I was wondering, I had heard that cancer skips a generation. Do you know anything about that?
Oh, yeah.
My mother and her 3 sisters all died by 42 of cancer.
Sure.
I had lung cancer, but yet my sister's okay. So
Yeah.
I'm throwing it out there at you.
Yeah. It's a great question. There are a lot of different risk factors that go into a person's risk for cancer. One of those strong risk factors is genetics. So it's truly what's in your DNA, and it gets passed down from your parents to you and your siblings. There are certain genes that if you inherit a mutation in one of these genes, your risk for cancer in your lifetime is very high. You've all heard probably of the BRCA1 and BRCA2 genes. Very famously, Angelina Jolie has a mutation in the BRCA1 gene, and as a result, her mother died at an early age of cancer. And so Angelina Jolie, decided to undergo a pretty dramatic intervention, which is she had a prophylactic mastectomy, she had her breasts removed, and she had a prophylactic oophorectomy, she had her ovaries removed. And so that's because she wanted to get ahead of that risk. When you do have a genetic risk for cancer, it means that you have one copy of that gene that's been mutated that you inherited from one of your parents. If you have one copy, you have a 50% chance of passing it down to all of your offspring. So that means that 50% of those offspring potentially also have one copy, and 50% of them don't. And the ones who don't won't have that same inherited risk for cancer as the ones who do. There are other risk factors for cancer that are also shared within a family. Your environmental factors also are shared with your family unit. Where you live, what you eat, what your circadian cycle is, all of this is shared within your family unit. And so we also know there are environmental factors that are also shared within a family. There are things that we can do on the environmental side. There are all sorts of behavioral modifications that we can undertake to ensure we're decreasing our risk for cancer. The number one thing is to not smoke, or if you are a smoker, to stop smoking, if you stop smoking, to be screened for lung cancer even after you've quit. There are other things like diet and lifestyle modifications, having a healthy BMI, ensuring that you are limiting your intake of alcohol, and then also ensuring that you're limiting your intake of red meat and processed meats. I know this is like not the right venue to say this. But But we know there are lifestyle changes that we can undertake to be able to help.
I'll add one that might help a little. So the BMI one's really interesting, and you might not actually need to lose the weight, and just doing the exercise is okay. It's really hard to lose weight, but moderate physical exercise is basically better than any drug we have. So there's been many studies coming out with all sorts of cancers now, large groups. And so one of my doctors, he tells his doctor, that he tells his patients, we can't work together unless you're willing to undergo some moderate physical activity to try to do it. We're going to fight it together, and that's one of the best things you can do. And you don't have to lose the weight. The activity's enough, which is very interesting.
Thank you so very, very much. This has been so touching to so many of us. And as I look around this room, I can see so many tears. We have all been touched in our families by one or two more instances that are very, very dear to our hearts. And right now, in my tears, I am thinking about my parents. Now, I apologize because maybe this is a repeat question to you, because I think you've just answered my questions with your finishing sentences. But in my parents' age, that was a no-no word. Nobody had cancer. They lived to 96 years of age, both my parents, both my aunties, and not so much my uncles. And I'm a farm girl. What is it today's in our diets that our children and young women and young men are getting cancer so early? What are we all contributing to this society of cancer? Thank you so very much.
Yeah. It's a great question. I mean, what we know statistically is the reality is that actually we have seen cancer mortality decrease over the last several decades. As I mentioned, since 1991, we've seen a 34% decrease in cancer mortality. However, there are some risk factors that are more part of our modern society that folks are starting to study. One of the things that we know is incredibly important, and there have been some really interesting studies about this, is the role of your gut microbiome in your cancer risk, and also in your ability actually to respond well to immunotherapy. We also know that there are all sorts of pollutants that have been human-made, including things like microplastics that might be contributing as well. The reality is that the epidemiology of this is still being studied. There is not a clear answer on this, but these studies are ongoing. And what we do know is that it's something we have to think from a systemic level. So it's not something that we're trying to identify a single thing. We know that there's multiple risk factors that are happening, contributing. And so now the studies are really thinking about, from a systemic level, why are we seeing this increase in earlier onset, especially colorectal cancer, and breast cancer is the other one where we've seen that increase. So it's a little bit of a mystery, but it's something that folks are actively studying.
The other thing is we know a lot more now. So when someone dies of cancer, we know exactly what type and what they died of and what it was and how it killed them. And in the past, we didn't always know that. We didn't know what type, and sometimes it was just nondescript, and it wasn't given the name. One thing that's really interesting is America has more prostate cancer than Europe, but it doesn't. We screen more for prostate cancer, so we find more prostate cancer. We started looking more, and our patients do better because we have more, but we find everyone and treat them earlier. So some of the perception of the increase in cancer is we're just finding it more, we're finding it early. And what Alicia said before is finding cancer in a young person is often a good thing, because if we find it when it's really early, we can do something. If we waited 10 more years, it might be too late. And so as we change our monitoring, we see different things, and some are going up. Alicia said it, pancreatic too is going up. So there are things to work out, but by and large, it's coming down.
All right. Maybe we'll take, I know we're standing in between you and dinner, so we'll do maybe 2 more questions, and then please feel free to come and find us afterwards. We're happy to answer individual questions.
Thank you very much for all your work, and thank you for coming here to Sailfish Point and raising awareness. My question is on the funding side. How big is the federal government funding for cancer research, and how big have the cutbacks been? What are the implications, short-term, long-term, and how are you adjusting to that?
Yeah, thank you for the question. Yeah, this has been an evolving situation. So there have been a lot of disruptions to federal funding for all biomedical research in the United States, including cancer research. A lot of this ecosystem of funding is supported by the NIH. They are the largest and most major funder for biomedical research, including cancer research in the United States. What has happened is that because there's been this uncertainty in NIH funding, there have been very nuanced things that have happened. Some people's grants have been canceled. Many of people's grants actually were delayed. So they weren't canceled, but the payments didn't come on time. And then some people's grants that are supposed to be renewed kind of almost automatically every year were being held up in renewal. Sometimes for these folks, eventually their funding was released or their funding eventually did come. But unfortunately, when there's been a delay of multiple months, 6 months, 8 months, between your last payment and the next payment, there's enough uncertainty that it has caused there to be a disruption in the workforce for biomedical research. It means that there have been some trainees and students who have decided to stop their training or to leave, go to Europe, or to leave biomedical research and go into a different vocation altogether. And that's incredibly unfortunate. I've spoken to many of our investigators at CRI, and I think the resounding thing that everybody has said is we have to make sure we're investing in earlier career trainees. Maybe this is a blip in terms of the NIH funding uncertainty. Maybe it will all come back. Maybe it'll be fine. If that is true, we will still have destabilized a very key generation of trainees who are in this vulnerable state in their training pipeline and maybe made a decision during that key moment that would change their trajectory for their career. So for that reason, that's why we decided what we had to do was to double down on our early career researchers. So we actually last year drew out of our reserve fund in order to fund more postdoctoral fellows. For this year, as I mentioned, we have more than double the application numbers, and we are committed to still funding as many of those postdocs as we can. And then one of the things that I heard last year from our faculty was that they were really worried about the postdocs who were about to hit the job market. They were about to go and find themselves their first independent junior faculty position. But because of the timing of the federal cuts, even the most promising ones were gonna have a hard time finding a job. And so what we did last year is this year we launched our Ignite program. So this is our first year with Ignite. Ignite is a funding mechanism that will give up to 2 years of postdoctoral funding, followed by 3 years of independent faculty research funding, if that person is able to get a faculty position. And this is really to double down on these promising postdocs who are gonna become the principal investigators of the future, making sure that they don't quit at this very, very vulnerable time. So we're actually going to be welcoming our first class of Ignite awardees this year. Haydn's actually reviewing those applications for us right now. We had an overwhelming number of submissions. We're really excited to be awarding those in March.
I think many of you have worked in business for a lot of your lives. Imagine when you become very uncertain what your money is going to be like for the next 2 or 3 years. You have wonderful people who work for you. You want to keep everything going. You stop taking risks. You stop dreaming of big things that you might do. We stopped some stuff. We were like, okay, that's expensive and risky. let's make sure everyone keeps their jobs. Our money didn't change, just the perception that it might change was enough to throw us off. We got through it, having CRI being rock solid was fantastic for us. I did better than friends, but the uncertainty is what is the problem. We need clear, this is not an issue that needs to be argued about. Nobody wants more cancer. Everybody wants us to work on this. I've never run into anyone who doesn't think that. So certainty is what we want. And you'll notice the NIH was funded at the rate that they asked for, NCI as well. I can tell you it was because of a lot of pressure on senators and House members. And if you call people and say that you really care about cancer research and this should not be political, why are we arguing about this? There's many other things to argue about. This one we all agree on. It makes a really big difference, and that was what swayed it. The House and Senate were very happy to fund this because of people calling and saying, we believe in this. So we felt very supported and good. Thank you.
We'll do one more question if there are any. All right, I think maybe we exhausted your questions, or you're just very, very hungry. I'm going to hand it back over to Jane.
Hi, so I'm Jane, and I hate cancer. Cancer took many years, good years of our lives. My husband was stage 4 cancer. We lived it, and we won. That being said, we were lucky. We were really lucky. They just shoved everything in him, and one of those drugs worked. He was quickly followed by our son, who loves sailfish more than you could ever remember. He married here, and he came here every single time he could, and he is the reason I am here. He was a golfer, so he loved the golf course. I want to thank all of you. I want you to understand what this means to us. It means so much. Our son only wanted to save lives, and I'm hoping that I made him proud, and my husband made him proud, because we didn't cave. We're still trying to save lives. Recently at the Plaza Hotel, we were recognized by CRI for a very prestigious award, the Oliver Grace Award, which is for promoting research. And I would now like to take a moment and tell you, I now take this award from my husband and I because you are the recipients, not me. You must understand that Dick and I may be a flame, but you're the fire. We need you, and we'll always need you. And I can't tell you how grateful we are for you. And for all the people who could not come tonight, and there are many who still to this day in Connecticut and here still donated, what can I say? I will end with a song, which I always try to do. And I would ask my family to come and thank you to all of you personally as we just go around the room quickly. Light your candle, light it for somebody that you know who maybe could not be here for any reason. And let us personally thank all of you. Thank you. And the band will start.
There's a calm surrender to the rush of day when the heat of a rolling wind can't be turned away. Unenchanted moments, and it sees me through. It's enough for this restless warrior just to be with you. Can you feel the love tonight? It is where we are. It's enough for this wide-eyed wanderer that we've got this far. Can you feel the love tonight? I was made to rest. It's enough for kings and vagabonds. Leave the very best. There's a time for everyone, if they only learn that the twisting kaleidoscope